All right, cool. All right, and my track is all working. Well, the final stretch of NDC. I hope you guys have all recovered from the hangover this morning. I know I had to take it easy last night myself. And so, yeah, thanks for coming to this talk. And I want to tell you about a story of how I helped a client build an AI-powered code reviewer. And importantly, some of the things that we learn about some of the practical limitations and challenges you have when it comes to building real-world AI systems, especially when you try to build a business around it, specifically, in our case, a business to customer B2C situation. So in terms of the AI code reviewer we build, as soon as you create a PR, we're going to get notified, and our AI robot is going to look at your PR, going to scan your files, analyze them for potential problems. It could be coding anti-patterns, it could be security vulnerabilities, it could be any number of things that the AI model is able to pick up, which is surprisingly a lot, far more than what I can pick up myself. And so when we see there's a problem, we're going to tell you, we're going to put a little comment on the line that we identified there's an issue. We're going to tell you what the problem is, what kind of impact it has, and also give you some references to, I guess, industry best practices, things like OWASP, or in this case, what did we find out? We found that you're using a library called the JS YAML, and you're loading a YAML file, which can potentially coming from an untrusted source, and you may be unsafe. So we give you some helpful suggestions on how you can fix it. And with GitHub, you can also just click the button, and you will automatically commit the change to your PR and update it, which can be really useful. If you agree with what our AI model has suggested. Of course, that's the kind of the back-end side of things, the workflow side of things. There's also a front-end website you can go to, evalua.io, where you can see a history of all the repos, all the PRs that we have scanned to tell you that, hey, we've identified X amount of critical problems or minor issues and things like that. You can start with a free personal account, but you can also then upgrade to an organizational account where you can pay for a license, invite your team members, so you all have access to the same server repositories and be able to run AI code reviewer against your repos. And of course, you can add your repos or you can remove them depending on which repos you want us to analyze your pull requests. So in this talk, I'm going to tell you kind of how we built it. I'm very much an AWS specialist, and so I'm going to show you our architecture in AWS, but I'll tell you how these different services can translate to Azure, because pretty much you're going to get one-to-one, I guess, equivalent in Azure as well, and specifically why we chose to use Serverless and also Amazon Bedrock. But the bulk of the talk, the meat of the talk, is about a lot of things that we learned along the way, both in terms of how these LLM models work, their limitations, but also from a business point of view, some of the real-world challenges you're going to come across. So the team itself was very small. Essentially, I built all the back-end stuff, and the client, Sam, he did all the front-end work around the website, and we basically worked together. And in the title, I mentioned that we did this in 80 hours because I know exactly how many hours I charged Sam, so I know exactly how long it took me, at least, on the back-end side of things. And we got something working, like a quick demo initially, I think the first 5 hours, but I'll tell you later in the talk, there's a lot more things you probably don't think about from that point on. It's very much the 90-10 rule, where you get 90% of the thing done in the first 10%, and then the last 10% is where all the user experience or the developer experience, all of that stuff is take up most of your time. The goal of the project for us to launch something, to start testing against the market, see if there's any, I guess, interest in this kind of thing, and can we do something that's going to be sustainable as well. And of course, we want something that's going to take really no maintenance. So that's why we also chose serverless. And of course, we want something to be cost efficient. And if we happen to strike gold, we also want to be able to say, okay, this system can actually scale to many, many users. And of course, what is cost efficient at, say, 10,000 users may not be cost efficient when you have 10 million users. Of course, on the back of our head, we're always thinking about, okay, if we get popular, we happen to strike gold. What do we need to do to re-architect to make the system cost efficient again? So my name is Yan. I've been working while building stuff on AWS since 2010, and I've pretty much focused around the serverless spaces since 2016. Nowadays, I kind of help the Lumigo team with things like this, speaking at conferences, but I work as an independent consultant where I help other companies. And sometimes that means training, sometimes it means helping a customer to launch an MVP and build whatever it needs to be built for that. So quickly about the architecture. So the whole thing kind of tied around the webhook so that when you create a new pull request, we get a webhook from GitHub. And so we have a webhook API that handles that. So a lot of the AI stuff is happening over there. So behind the scenes, this webhook API is running on AWS using API Gateway and the Lambda, which just gives you a REST API, and you can run your serverless functions there. But we don't want to process and do all the analysis right there instead, because the webhook needs to respond within 2 seconds. So instead, we take whatever payload we receive from the webhook, we save it into an event bus so that we can process it after the fact. And for those of you who don't work with AWS, essentially EventBridge is on Azure, you have Event Grid, and Lambda on Azure, you've got Azure Functions, and API Gateway is kind of the AWS equivalent of API management. So once we have those payloads captured as an event in our event bus, we can then use that to trigger a function to then say, okay, pull request has been created. Let me go ahead and analyze this. And we can call Bedrock, which is a service that AWS offers that allows you to run different models, and you get charged for them based on a token, how much token you're using on the input and the output. And once we analyze your files, your pull requests, we can then save those results into a database so that we can then surface that information in the UI. In this case, database, we're using DynamoDB, which is Amazon's NoSQL document store. Of course, on Azure, you've got the Cosmos DB, which would be a close equivalent. But we also have fallback to using Anthropic's API directly, as well as other models that we may choose to use in the future. So on the front-end side of things, we've got a website, of course, and for us to show all the information, we want to tell you about the different repos you have, the problems we found. We have a GraphQL API, which just makes it easy to stitch different kind of entities together in a single response so that when Sam is developing the front end, he can easily access different pieces of information we have. And all of that is going to Lambda functions or the DynamoDB tables. And for user management, we're using Clerk, which is really useful in this case because it supports things like organizations and invitation flows and adding members, including the UI components. So in terms of getting something out there quickly, it was really useful to be able to just drop in this UI component and then have some integration on our side to then make sure that when a user logs in and calls our API, we are authenticating your token against Clerk to make sure that it's valid. And whenever a user creates a new organization, we get notified via webhook. And of course, there's the GitHub webhook as well. And for payment, we're using Stripe. So that's basically the high-level architecture. But most of the stuff is actually happening, all the smarts are happening in essentially one Lambda function. That's where we take your pull request, we fetch information from GitHub, and then we use AI models to analyze them for problems. In terms of the challenges, the main one is that we are dealing with customers' source code, which are really sensitive information. We want to make sure that everything is treated in a way that's secure. And we also have pull requests of all kinds of different sizes. Maybe a large pull request with thousands of files that's been changed, or maybe a single file with thousands and thousands of lines that have changed as well. So we talk about how kind of that pushes us against a lot of limits in the different services we use. And we decided to use Amazon Bedrock as opposed to using OpenAI or some of the other LLM providers. A big part of that is because, well, it's there in AWS, so it's easy, but also because of security. With Bedrock, they're going to encrypt your data, and in the privacy argument policy, they say clearly that they're not going to use your data to train other models, nor will they sell your data to other providers. And this is important to us because we also consider other models, including DeepSeek when it came out. But soon after DeepSeek came out, this also happened. And I can't stress enough how much we don't want something like this to happen to us, where DeepSeek had, the ClickHouse database was publicly exposed, so anyone could have seen all the chat history from anybody in the world. And so with Bedrock, again, in the privacy policy, they clearly say they're not going to share your data with anybody, so that's important to us. But because we also have fallback to other providers in case something happens with Bedrock, it's not available, or we're getting throttled, we also need to make sure that providers like Anthropic has also similar levels of privacy in terms of protection. So, and as far as I can tell, they do. They're not going to share our data with anybody else. In terms of serverless, we like the fact that Bedrock gives you two different pricing models. One where you just pay for the number of tokens you use, and that's great when we are starting out because we didn't expect to have, say, 10,000 people sign up on the first day. So at the low throughput, that actually works really well for us. But as you have more and more users and you have a more predictable traffic, then you can also switch over to the provisioned throughput pricing as well, whereby you can pay a fixed amount for a certain amount of token usage. And if you have a fairly predictable usage pattern, then that is much more cost efficient at a per token level. And pretty soon after we launched, I think at the end of last year, also DeepSeek came out and a few other models came out as well. And then Bedrock also added DeepSeek to their platform, and you can also pay for DeepSeek R1 and on both the provision, but also the token-based pricing. And if you compare the models on Claude with DeepSeek, you can see that it's actually quite a bit cheaper compared to using Claude on the Bedrock. But it's still more expensive than if you just run Bedrock yourself or use Bedrock's API directly. And the difference mainly is just that, with AWS, they provide better security and operational, experience, because I can't stress enough, we don't want anything like this to happen to our data for them to be exposed. And the Bedrock also has got a few other things out of the box, like a managed RAG or retrieval augmented generation. It's got agents, it's got guardrails, as well as model evaluation as well. And we did some quick evaluations in the first place when we tried to choose which model we want to work with. And based on the evals we had, Claude Sonnet was by far the best model at the time. But since then, Gemini 2.5 came out, and that actually works really, really well, and as well as a few other models that came out. So to the main, the lessons that we've learned, what we actually built is pretty simple. We actually got something out pretty quickly. It's a bunch of webhooks. We analyze your file changes, and then we give you some feedback by telling you which lines has some problems and how to fix them. And if you look into Lumigo, which is the observability platform, I can see that, okay, when a webhook event happens, it triggers my Lambda function, and we did a bunch of things. And the most important thing is here that, after we save the event into event bus, that triggers another function. We have to call lots of different APIs to get the file from GitHub, to analyze them, to save data in database and things like that. And when it's a large PR, we have to make a lot of different APIs calls. And that actually causes our function to time out, even when we use a maximum 15 minutes for our function, because all those APIs, they take time to respond. And the AI models, they also take quite a long time to run as well. To analyze a single file, for example, single request to Sonnet would take, say, 20, 30 seconds to respond. The good thing with Lambda and EventBridge is that you actually get built-in retries, so that if you fail the first time, it gets retried automatically. And because we've got all these checkpoints, essentially idempotency keys for different bits of work we've done, so that on a retry, we're going to skip over all the files that we've analyzed and already checked, so that you just move on to the next bit. So normally on a retry, it just fixes itself. But what we found is that we end up running into a lot of different limits in terms of the limits with the LLMs, APIs, with GitHub, with AWS, And so even though we're building this system around AI, we found that there's still a lot of software engineering involved. In fact, the actual AI bit is probably only about 10% of the problem. And that's something that a lot of the other people have said as well, that, okay, there's still a lot of software engineering in terms of connecting the data you have in your system into the LLM. And of course, me and Sam, we both use AI code assistants like Claude Code and the Cursor very heavily as we're building Evalua. And we're also using Evalua to then review our code to find lots of problems. And this actually works really well. This is like really nice synergy here because AI is really good at finding problems that AI-generated code has, just not at the time it's writing them. So we keep finding that, okay, we generate some code, we can create a PR, and then pick up all these problems, and we're like, it's the same model we are using to do both. Why can't you just not do those problems in the first place? There's also a funny story as well that after we launched, another platform reached out. They're like a vibe coding platform. So I think they had like 10,000 customers, mostly non-technical like founders who are using these tools to generate applications. And the founder for this company told us that our customers create all these AI slop with all these security problems. We want to partner with you because you're going to be really good at finding those problems before it goes into production. And we're like, great. Of course, they didn't want to pay for it. They said, oh, yeah, you guys are going to get 10,000 potential customers. That's your kind of upside. But I was going to talk about the financial side of things pretty quickly. And we looked at numbers. OK, this is going to bankrupt us in like 2 days. So, of course, that was the no-go for us. And one of the big things that we found was that different models, of course, have got different pricing. That's one consideration. A lot of the time when you're reading about different, from the social media, people talk about different models. They focus on the reasoning capability of these models. But I think when it comes to actually building AI systems, a lot of the other stuff are probably even more important. Things like the size of the context window, how much response token you can use at one go, and API rate limits. And the context window for us is important architectural decision because it also affects us in terms of, do we just give all the different files in a single prompt, or do we prompt one file at a time? And one of the things we learned pretty quickly early on is that the context window that's published is mostly a lie. Now, you've got all this model that says they can do a 1 million token context window, but if you, at least at the time, if you try to upload, say, a PDF file, and it's asking a question about, okay, what's in my PDF file, you find that you get a lot of hallucinations. Turns out what happened at the time, we didn't know this at the time, but later on, there's a new benchmark that came out that specifically tests for how good a model is at reasoning with a large context window. We found out that most of the things that's out there, a lot of papers about new models, they use the same retrieval needle in a haystack test to test how well it's able to retrieve information from a large context window. And a lot of models do really well on this test. But it turns out whether or not you're able to recall a piece of information from a large context window is not really related to how well you're able to reason with the data in that large context window. I guess about a couple of months ago now, a new benchmark came out called the Fiction Live Bench, which was designed on testing a model's ability to reason with large context window. And pretty quickly you see that most models, it just falls apart in terms of its reasoning as the context window gets to about 32 kilobytes. Even though some of these models can handle 1 million token context window, they can't actually reason with the data once it hits about 32,000. Except for a few models, mostly the more recent ones like Gemini 2.5, GPT-5, and the Grok 4. Up until some of the more recent models, the other models pretty much can't handle large context windows, even if they allow you to use them. Which meant for us at the time that we were working with models that pretty quickly falls apart as we give it a big file to analyze. So it made us made a decision to basically analyze one file at a time in order to make sure that we still get a pretty good accuracy in terms of what our code reviewer is generating. So there's also a lot of other things to consider as well. Cost is a big one, especially if you are doing any kind of a business around AI systems. And if you're building for internal enterprise use, you probably don't care about cost quite as much as we do. And also there's performance as well, all of which are things you've got to think about when it comes to model evaluation. And one that was, I guess, particularly annoying is the API rate limits, because with Claude 3.5, the default throughput limit is only 50 per minute, not per second, per minute. So because we made a decision to analyze one file at a time, it meant that we can really easily run into a situation whereby a single PR is going to exhaust all of our available throughput for the whole minute. So nobody else's PR is going to be able to, is going to get analyzed in that whole minute. With Bedrock, you can actually raise this to 1,000 per minute through a support ticket. And you can also use what is called a cross-region inference. Essentially, you can use two different AWS regions and basically to double your throughput. And we're doing both, of course, but we also have to do a few other things. So, for example, to limit the number of parallel requests we make for a single PR, basically some kind of fair usage, whereby we don't allow one PR to consume all of our available throughput, so that no other customers can get their pull requests reviewed in the meantime. But also importantly, we have fallback to other less powerful models, but models that have got higher throughput limit, which allows us to, okay, if we can't use the best model right now, we can use other perhaps cheaper, but also more abundantly available models as well, including falling back to using Anthropic's API directly. You've been able to use other models is also good for cost control, and that kind of brings me to another big lesson is that, well, if you're worried about unit economics, the LLMs are still quite expensive. And you see this with a lot of other developer tools as well, from people that are kind of self-funding it or bootstrapped, where they often find that a single customer can use up a lot of your available budget. And even companies like Cursor, which is the fastest company to hit a million ARR, sorry, 100 million ARR, even they had to raise their prices recently, and they gave the reason that, well, oftentimes you find that customers who have large pull requests can use up a disproportionate amount of usage, and of course, those cores to LLMs are still quite expensive. Even though over the last couple of years, the prices have kept coming down on a token level. So the token costs have come down significantly, but we also find that with the newer models, especially the thinking models, the reasoning models, they output much more token because they also output their thinking. So overall, your cost might still be going up because even though per token is cheaper, you're just generating a lot more tokens. And of course, the fact that everything can't just be AI, LLM anymore. It has to be agentic. You have to have all these smart in your models that knows, okay, I can't handle this request. I'm going to have all these different agents so that you got your initial, I guess, ingress agents that decides who to hand the request to have more specialized agents. And so eventually, beginning, you may have something like this, but eventually you might end up with exactly where we are with microservices, with so many agents, you can't even make sense of it anymore. So both in terms of the newer thinking models, but also in terms of the whole move towards agentic systems and having lots more prompts and data we're setting to AI models, you're going to find that the total cost is actually going to keep going up because of how much we're building more complex systems now using these LLMs. And that kind of circles back to, okay, if you're building a business, especially a B2C business, by building on top of these LLM models, then, well, it's really difficult to build a sustainable business model. When you're worried about, okay, well, if I can only charge the customer $10 a month, and in a single PR, they can potentially just blow through the whole $10 worth of token usage, then this is going to be really difficult to scale. For B2B or for enterprise use cases, you probably don't worry about this quite as much. But of course, this customer was bootstrapped, and we want to build something that is sustainable. And that also meant we have to we had to make a couple of architectural decisions to help us control the cost And for one of them is that we only analyze the changes in the file as opposed to the entire file, which turns out to also be good for user experience, because one of the very early feedback we had was, we were initially analyzing the whole file, but of course, we were finding problems that are not related to what you've just changed. So a lot of customers telling us that this is great, but you're telling me about all these problems that wasn't caused by me. Somebody else wrote that code 6 months ago, and you're telling me to fix it now, which is kind of annoying. So by only analyzing the changes that you've made, we kind of remove a lot of those noise. Of course, it also means that we can't do as good a job in picking up all the potential problems that you may have in your code base right now. We also have to limit how many pull requests we analyze for each customer, for the free customers at least, customers that are not paying for usage yet. For customers that were paying us, we do give you, that's a pretty generous limit in terms of how much you can use per month. But also, another important one that was, I guess, more on our side is, if we got an event from the webhook and we analyze them and it fails and it retries, we also don't want to be reprocessing files that we already analyzed in the past, and that's where some kind of an dependency control or checkpoint is important, both in terms of being able to succeed on a retry, but also in terms of cost control as well. So this way, if we couldn't process the whole thing the first time around on a retry, we can do that. But when we do that retry, we want to make sure that we're not going to call the LLM and pay for those tokens again on analyzing the same file multiple times. So this is where we have simple checkpoints. So every time we do something that has a side effect, for example, analyzing the file or writing the results to the database or to make a comment in GitHub, we want to make sure that we have some kind of idempotency token so that next time when we retry, when we process the same pull request again, we'll just blast through that. We get the result from the last time we did this, so that we know exactly what the problems are. And if there's something that we have to put a comment against GitHub, we're also not going to duplicate any comments on the lines as well. So for folks who are on AWS, you may be thinking, why don't you use step functions, which is an orchestration engine service that AWS offers. I guess on Azure, you've got durable functions. You've got something very similar that allows you to implement like a workflow using, Azure functions. The reason why we don't use that is because checkpoints is just simpler. And also, if we were to turn what we had in our Lambda function with all the different things you were doing into a state machine, then we end up splitting up your business logic across both the Amazon state language and your JavaScript or TypeScript code. So it becomes harder to reason with as well. And that then takes us to the next thing we learn is that latency is still a bit of a challenge. It's still, this calls to the LLM models are still quite slow. At least at the time, we were seeing that single request would take 10 to 30 seconds to respond. And that also means that, when it comes to Lambda, which charges you based on per millisecond of time that you're running, it means that we have all these CPU cycles that we were paying for, but not really using. So we have lots of wasted CPU cycles. So of course, that's not great. And one of the things we wanted to do was to say, because we are analyzing all of these projects, we can actually do some static analysis. For example, if you're using Terraform, we can actually run Chekhov or other tools to do some static analysis on top of what we ask the LLM models to check. So we can actually use those tools while waiting for the LLM models to respond. So there's quite a few things we can actually do and make use of the CPU cycles that we have. Maybe even do some crypto mining. Maybe just get some crypto money back in the meantime. And lastly, hallucinations was still something that we ran into regularly. We asked Bedrock to give us back the response in JSON so that we can turn the response into a nicely formatted GitHub comment. And 99.9% of the time is fine. We can take the response and then turn into good-looking comment. But every now and then, it just goes, nope, here's a plain text response. You go deal with it. Luckily, these kind of things are quite easy to catch. You get a response back, and you try to JSON parse it, and it fails. So this didn't work. So you can just fix it by running the request again. And on a second request, on a second time around, the model is going to give you back a JSON as you intended. But there's also other hallucinations that are a little bit more difficult to catch. For example, sometimes it will give you back a reference to some kind of, I don't know, OWASP link or something like that just didn't exist. It just made it up on the spot. And or give you a URL that just doesn't exist. We can still catch this. We can just do a curl against the URL, see if it actually exists. If it doesn't, we can also just remove that from the final comment we make to GitHub as well. And other times, you also just imagine, well, it just comes up with line numbers that wasn't in the commit. So for GitHub, when you want to post a comment against a line, you have to provide a line number. And if that line number doesn't exist in the PR, you're going to get an error. So again, we don't know if that problem was supposed to be on a different line number, but most of the time, it's just easier. It's fine to just ignore this and just admit this, that if the line number doesn't exist, okay, fine, we're just not going to tell you about this thing. So those are hallucinations where the model just makes up stuff that doesn't exist, which are really annoying. But there's also places where it's just not accurate because the information you give it is not complete. So the example I gave you earlier, where we picked up a security vulnerability where because you're using JS YAML to load the YAML content, it's potentially it's risky, allows someone to execute arbitrary code. The good news is that this problem doesn't exist anymore because it's been patched in the previous version of the library. The problem is that, because we're analyzing one file at a time and the model has no context of the entire code base as of the commit of the pull request, so it's not able to catch this kind of problems. So this kind of inaccuracies can actually be fixed by giving the model access to the entire code base. We can say, hey, here's the lines I've changed in this file, and here's the entire PR code base as of this pull request. Can you make sense of this? For example, if you got some kind of an agentic system for doing this, then the agent can decide, okay, right, I'm looking at this line of change. I need to go figure out what version of JS YAML the user is using. And then for this particular version, check, is this still a problem or has it been patched already? Then you can catch these kind of problems and you wouldn't flag them as a problem in the report, in the output. We kind of know how to fix this kind of inaccuracies in our response. The problem again goes back to economics. Well, our version, the MVP, was just doing straight up prompt engineering, and at that point, we already find it difficult to build a sustainable business around our usage of AI. Even though we know, okay, RAG can fix our problem, or making a more agentic system, code reviewer will fix the problem, but then again, that means the cost per request is going to go through the roof as we build a more complex, more sophisticated AI system. And this is where I guess companies like Cursor, all these other companies, they are just losing money on every single request. I'm convinced that the whole industry is just losing money. The LLM providers are losing money. People that are building on top of the LLMs, they're also losing money, even though they're making record revenues. Essentially, nobody's making money when you're building at least when it comes to developer tools, maybe there are other more, I guess, general public-facing tools that are profitable, but I'm pretty sure the companies like Cursor are losing a lot of money, and they're all relying on investor money to just keep pumping in and keep them going, and eventually, hopefully, they're able to charge everybody $200 instead of $20 because $10, $20 a month is just not going to be enough to pay for a lot of the AI usage. So those are lessons we learned in terms of what it's like to build AI systems in the real world. And the big ones, I guess, is the context window size. Yes, the model may say it can handle 1 million tokens, but make sure you test it first to see how well it actually handles the context window as it gets bigger. If its reasoning capabilities drops down significantly, it may mean that, that context window, you just can't use them. And if you're building anything that's B2B or B2C especially, then making sure that you understand the economics. Or if you can find a VC to fund all your losses in the meantime, then good for you. Also, in terms of latency and developer experience, latency is still kind of iffy. It's getting better, of course, all the time, and also hallucinations. That's where you want to do a lot of evals. Make sure that you choose the right model. And in terms of coding, we also find that Sonnet was probably the best one we found at the time. And since then, we've tested Gemini 2.5. It's great. It's great. And but for different languages, it performs really differently. For JavaScript and Python, a lot of models we tested do a pretty good job, pretty much all of them. But when it comes to Java and .NET, or maybe Rust as well, the performance drops down significantly. I think a lot of these models are not trained on as much Java compared to, say, JavaScript. And so in terms of their ability to code in those languages, but also in terms of identifying problems in those Java or .NET applications, is significantly weaker compared to Python and JavaScript. Okay, so those are the lessons we've learned. I know we still got about quite a bit of time. So if you guys got any questions, feel free to ask them now. If not, then hope you guys have enjoyed this, and yeah, enjoy the rest of NDC. Okay, thank you.